we're going to cover Chapter 10, Section 3, and today we're going to be learning how to use chords to find missing parts of our circle. So here is our first theorem. It's called the congruent corresponding chords theorem. And what this theorem states is that in the same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So if you notice here, it's got the words if and only if. So what this means is it can go either way. So they can either start by giving you that the arcs are congruent. So here, if they tell you that AB, this arc, is congruent to arc CD, then you can conclude that the corresponding chords are congruent. Or they could have started out by telling you that chord AB is congruent to chord CD, and then from that statement, you can say that arc AB is congruent to arc CD. So they'll start out by giving you one or the other, and that's because of the words if and only if. So the next theorem is called the perpendicular chord bisector theorem. And this one states that if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. So here we can see that segment EG is the diameter. It's going from edge to edge and it's going through the center. And if that diameter is perpendicular to a chord, and I can tell it's perpendicular because of the right angle, then that tells me that segment HD here is going to be congruent to HF, and arc GD is going to be congruent to GF. So if that diameter is perpendicular to the chord, it is going to bisect the chord and the arc. So the next slide has the converse of the perpendicular chord bisector. And this one states that if one chord is a perpendicular bisector of another chord, then the first chord is a diameter. So in here, because I can see that QS is a perpendicular bisector of TR, then that tells me that QS is going to be the diameter. Remember, a converse switches the if and the then statement. And then the next theorem is called the equidistant chords theorem. And this one states that in the same circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. So notice again the words if and only if. So this can go either way. So either they're going to give you that the chords are congruent, like they've done here. They've shown us that AB is congruent to CD. Then you can conclude that these chords are equidistant from the center. And that's what they're showing here, that EF equals EG. Now, you could have also been given that EF and EG are equal, then you can conclude that the chords are congruent. So they'll either start by giving you this, and then you can conclude that they're equidistant, or they're going to show you that they're equidistant. And remember, a distance always needs that right angle. If they show you that these segments are congruent, then you can conclude that the chords are also congruent. Now, when this occurs, this equidistant segment is a perpendicular bisector. So it's splitting that chord AB or CD into two congruent pieces. It's bisecting it. So on this example, for all three pictures, they want us to find the values of X and Y. On example 1B, they also want us to find an arc measure. But let's first zoom in here and let's take a look at 1A here. Now, if this 13, and I know it doesn't look like it's the same, but remember that wherever you have a radius, so if the radius, remember it goes from the center to the side. So this 13 is going to be the length of the radius. And remember, no matter where I draw a radii, whether I draw it this way or going this way, all of these segments are going to be congruent. So no matter where a radius is drawn in the circle, it would always have the same measure. So this over here is going to also be 13. Now, in this triangle, if you notice, we've got a little right triangle formed right here. And we know two of the sides. We know this side over here is the 5. And then because that hypotenuse of that triangle is a radius, we know its length. So now to find the value of x, all I need to do is Pythagorean theorem. So I'm going to do a squared plus b squared equals c squared. Remember, the c is always going to be the side across from the right angle, which is the radius, so it's going to be 13 squared. And then it doesn't matter if the 5 is the a or the b. So I'll just say the a is going to be the x, and then the b will be the 5. I need to square them. And then I'm going to subtract the 25 from both sides. I'm working on isolating that x squared. And then I get 144. And then I'm going to square root it. And that little value or that piece of the triangle is going to be 12. So x equals 12. So this is 12. Now, in order to find y, I could draw in another radius and then do Pythagorean theorem again. But what'll be the easiest way to find y is I can use my perpendicular chord bisector theorem. And remember, if the diameter of a circle, and that's this piece right here, is perpendicular to a chord, then it bisects the chord and its arc. So this tells me that x is 12 and so is y by using the perpendicular chord bisector theorem. So y in this picture is also 12. Okay, so notice in this particular picture, they've given us the measure of this angle right here. And this is actually a central angle. It's 60 degrees. I'm going to go ahead and pull this triangle out and sort of enlarge it because we're going to use our 9.2 knowledge of special right triangles. And I'm going to turn this into a 30, 60, 90. So this is 60 up here. Here's the right angle. And then over here, this will be my 30. So I've just pulled the triangle out because this is the 30 degrees right here. They've given me 6, the hypotenuse. Remember, you're memorizing that the side across from 30 is a, which is really where our y is. And then this is x, and this is supposed to be a square root 3. And then the hypotenuse is 2 times a. And that's what I need to solve for first. So I'm going to divide by 2, and a equals 3. So y is 3, because that's what a is. And then x is going to be a times square root 3, so 3 square root 3. So x is 3 square root 3, and y is 3. Now it also wants me to find the measurement of arc AB here. Now remember, we learned that the measure of a central angle is the same as the measure of its intercepted arc. So if I trace over the 60-degree angle, this is its intercepted arc. So if this central angle here is 60, so is this arc. And because this is actually, since this is a radius here, I could extend it and we can see that this diameter is perpendicular. So what I can use here, again, is my perpendicular chord bisector theorem. And because the chord has been bisected, so has this arc measure. So this side is also 60. So I could use my arc addition postulate, and to find the measure of arc AB, I'm going to add 60 plus 60, and it'll be 120 degrees. So for C, notice I've got two segments that are equidistant from the center to each of these chords. So if I use my equidistant chord theorem, I know that because the chords are equidistant from the center, they're going to be congruent. And I also know that this segment right here is a perpendicular bisector. So if this side over here is 8, so is this side. So x equals 8. But the whole chord is going to be 8 plus 8, which is going to be 16. And because those chords are equidistant from the center, this chord up here is also 16. So x is 8 and y is 16. And I used my equidistant chord theorem. So for example 2, they want us to find the measure of arc CD, which is right here. So if you notice that BD here, this is the diameter. It goes from edge to edge through the center. Notice it is perpendicular to this chord CE. So I can again use my perpendicular chord bisector theorem. And because the chord has been bisected by that diameter, I know that this segment is congruent to this, as well as the intercepted arcs. So in order to find the value of x, I'm going to set arc CD equal to arc DE, find x, and then plug it back in. So CD is 9x. DE is 80 minus x. Going to add x to both sides. I get 10x equals 80. Divide by 10, and x equals 8. Now, it didn't ask for x. It wanted the measurement of arc CD. Remember, CD was 9x. So take out x, plug in 8, and the measurement of arc CD is 72. Now, what you might be tempted to do, and don't do this, is notice you see a little right angle here. And you might have thought, well, why isn't 9x going to be equal to 90? That 90-degree angle is not a central angle. So that arc measure is not equal to 90. If that angle was at the center, then you would have set 9x equal to 90. But that 90-degree angle is not a central angle, so we can't use that 90 to find the arc measure. Now, let's change up the question. What if instead I had asked you to find the measurement of arc BC? So if you notice, since BD here is the diameter, we can see that we've got a semicircle arc here. And if I already know this piece right here is 72, and I know a semicircle arc is 180, I could subtract 180 minus 72, and arc BC would be 108. So again, be able to find the missing parts, whatever piece of the circle, whether it's an arc, a chord, that I ask you to find. This one is stating that in circle C, QR and ST equals 16. QR and ST are chords. So because I have two congruent chords, that can also tell me that these two segments that are perpendicular are equidistant from the center. So what I can do here is I can use my equidistant chords theorem to find the value of x, and then I'll plug it back in to find CU. So I'm using my equidistant chords theorem to find the value of CU. So because my chords are congruent, that tells me that CU is going to be congruent or equal to CV. So I'm going to take CU, which is 2x, CV, which is 5x minus 9. I need to solve for x. So I'm going to subtract 5 from both sides, 5x. 2 minus 5 is negative 3 equals negative 9. Divide, and x equals positive 3. Now the question didn't want x, it wants CU. So CU was equal to 2 times x. So I'm going to take what I found for x, plug it in, and the length of CU is 6. Now, you might get a question like this in the homework, and then they might change it, and instead of them asking you to find the equidistant segment, you might get a question where they'll say, now, find the length of the radius. Now, if you notice here, this CU and CV, these are not radii. They don't go all the way to the edge of the circle. But what I can do is I could draw in a radii and connect C to R. And now I've made a nice little right triangle here. And remember, this equidistant segment bisects the chord. So this is 8, this piece right here. And then I just found CU, it was 6. So now to find the radius, which is really the hypotenuse, I'm going to do Pythagorean theorem. So I'm going to do 6 squared plus 8 squared equals the radius squared. 36 plus 64 equals the radius squared. 100 equals r squared. Square root it, and the radius length is 10. What if it said find the diameter? What do I need to do now? Multiply by 2. So if they change it up and then they say find the diameter as well, all you do is 10 times 2, and that will give you the diameter.